it is a signal processing. So there are two kinds of signal in the industrial control system. One is the analog signal.
So what number is this?
I006. So analog signal is a collinear signal. Solid signals that we go, they are collinearly. This is the analog signal. Now one with the digital signal. The digital signal got only 1 and 0. So 1, 0, like this. So this is the digital signal. So there are two kinds of signal in the control system. One is the analog signal and another one is the digital signal. So the analog system called easier. Analog is easier. But the problem with it is each sensor external noise or interference or loading effect can influence the signal. This means if you are using the analog signal, the analog signals are subject to the noise, interference, and the harmonies. Those are the difference the disadvantage of the analog signal. So because of this one, when we are using the digital system, we need to the eliminate those effects. So digital signal, they are not subject to those interference. So this is why we use the digital signal system. So the electrical noise interference amplifier gain, loading effects they are influence on the analog signal, but they are not influence on the digital signal. This is why we need to change the analog to the digital signal. So that another way is digital computer they require the information, so that the information encoded in the digital format. So before it can be used. So this is the why we require to make the digital signal processing is analog signals are usually subject to the interference noise, but digital signals are not subject to the interference. So that by changing the digital signal, we can avoid any interference. And similarly, the digital signals are required for the digital computer to process. So this is why we need to use the digital signal processing. So analog information or analog signals are subject to the electrical noise, interference drift, amplifier gain, loading effects. In the digitally encoded signal, a wire carries either is a high or the low level and is not particularly susceptible to the programs associated with the analog signal processing. The digital computer requires the information encoded in the digital format before it can be used. So this is why we use the digital signal system. So that when we are using the digital system, so we use a number system. So there are the number system with the binary or the octet or the hexadecimal. So those are the number system. So number system binary with the base 2, octet with the base 8, hexadecimal with the base 16. So those are the number systems utilized for the digital system. Okay, so firstly we talk about the binary number system. So binary number we can represent. For example, and 10. So then you can see that an multiplied 2 power n plus an minus 1 2 power n minus 1 plus 2, and then go to the a3 2 power 3 plus a2 2 power 2 plus a1 2 power 1 plus a0 2 power 0. So this is for the mathematical format for the binary number system. Binary number system and then is equal to an 2 power n plus an minus 1 2 power n minus 1 plus a3 2 power. So this adding up to that a3 2 power 3 plus a2 2 power 2 plus a1 2 power 1 plus a0 2 power 0. So this is for the an. And so this is for the so in this case, and then it says a base 10 number. And also, and 2 is a base 2 number. So this is for us a base 2 is represented by the binary system, and base 10 is normally we use as a decimal system. So this is for the binary system. So if you use the base 8, then we use the octet system. Base 16 we use the hexadecimal system. Okay, so first we solve the problem here. Find the binary equivalent of 259 base 10. Binary equivalent of 259 base 10. So we have to find the binary equivalent of 259 base 10. So to find the binary equivalent, this one we have to divide it by the 2. So the first set of 259 is divided by 2. So that we use as a result is a 129, the remainder we use a half. So this means that you get divided 259 can be divided by the 2. So long as it can be divided by the 2, you can put the thing A0 is equal to 1. This is can be divided, you can put as A0 equal to 1. Cannot be divided, you have to put a 0. Okay, so this is the result we use 129. So this 129 is divided by 2 again, so that the result we use 64 and remainder will be the half. So from here you got that A1 is 1 because of the 129 can be divided by 2. So long as can divided by 2, you have to put a 1. So 259 can be divided by 2. Result is 129. Remainder is half. So that can be divided. So A0 is equal to 1. 129 can also be divided by 2. So the result is 64. Remainder is a half. So the A1 is equal to 1 because it can be divided. And also the 64 is divided by 2. So in this case, you got the thing. So in this case, so long as you get the remainder, you have to put the 1. So 259 divided by 2, 129 plus half. So long as the remainder is a half, you have to put a 1. And also, 129 can be divided by 2, so that 64 remainder is a half. So long as you got the remainder, you have to put a 1. And 64 is divided by 2, so you got it at 32. And remainder is 0. Because the remainder is 0, so A2 is equal to 0. And also you can divide it by the 32. So 32 can be divided by 2, so the result will be 16. Remainder is 0. Because the remainder is 0, A3 is equal to 0. And then 15. 15 divided by 2. So divided by 2 means, so this means the result is 8, remainder is 0. Because the remainder is 0, you put the A4 is equal to 0. And there's 8. 8 divided by 2. So that's 4, remainder 0. Because the remainder 0, A5 is equal to 0. And 4 is divided by 2. So that's 2, remainder 0. So this means that A6 is equal to 0. And 2 is divided by 2, so result 1, remainder 0. So A7 is equal to 0. Okay, so half.
1 plus 0.
So this is the result and remainder. Okay. So the finally 1. So 1 is divided by 2 cannot be divided. Only you got the remainder half. So because the remainder half, AA is equal to 1. So this is we got. Okay, so I say again. 259 divided by 2. So the result 129, remainder half. So remainder, because the remainder half, A0 is 1. 129 divided by 2, so result 34, remainder half. Because the remainder half, A1 is 1. 34 divided by 2, so result 32, remainder is 0. Because the remainder 0, A2 is 0. 32 divided by 2, so result 60, remainder 0. So because the remainder 0, A3 is 0. 60 divided by 2, so result 8, remainder 0. So the A4 is equal to 0. 8 divided by 2, so result 4, remainder 0. Only remainder is half. So the AA is 1. And then after you got the AA1, you have to rewrite again. Normally you write again the A8, A7, A6, A5, A4, A3, A2, A1, A0, and a base 2. So this means that AA value is 1. A7 is 0. A6 is 0. A5 0. A4 is 0. A3 0. A20, A1, 1, A0, 1. So that will answer will be there. 1, 0, 0, 0, 0, 0, 0, 1, 1, base 2. So this means that 259 base 10 is equal to 1, 0, 0, 0, 0, 0, 0, 1, 1, base 2. So this is way that we find that finally equilibrium of the 259 of base 10. Next one with the offset system. So offset system means the base 8 system. So base system is how we can utilize. So the binary system is n is equal to an 2 power n plus an minus 1 2 power n minus 1 plus a3 2 power 3 plus a2 2 power 2 plus a1 2 power 1 plus a0 2 power 0. So this is for the binary system. So n means the base 10 number. This is decimal. And 2 means the base 2 number binary. So firstly we have to find a binary that equilibrium of 259 base 10. So firstly you have to divide it by 2. So 259 divided by 2, so that's 129, remainder half. So we got the remainder, A0 is 1. And 129 divided by 2, so result 64, remainder half. So we got the remainder, you got the remainder, so this is the A11. 64 divided by 2, so result 32, remainder 0. So A2 equal to 0. 32 divided by 2, so result 16, remainder 0. So A3 0. 16 divided by 2, so result 8, remainder 0. So A4 0. 8 divided by 2, result 4, remainder 0, A5 0, 4 divided by 2, result 2, remainder 0, so A6 0, 2 divided by 2, result 1, remainder 0, so A7 0, the final result 1. So 1 divided by 2 is that there is no result, only remainder, so because the remainder are A8 1. So when we are right again, we have to write the A8, A7, A6, A5, A4, A3, A2, A1, A0, base 2. So that will be the, you substitute the value, so that will be the 1 0 0 0 0 0 0 1 1 base 2. So this is a 259 base 10 is equal to 1 0 0 0 0 0 0 1 1 base 2. So this is what is a binary function. And also the offset function. Offset function you can also calculate. And 10 is a base 10 is equal to you can calculate. So this is what is a d n a power n plus d n minus 1 a power n minus 1 and both, so this becomes as d2 a square plus d1 a plus d0 a power 0. So this is what is a decimal number. So enter a decimal number. Okay, so we solve another problem. Find binary n of decimal equivalent. 33 base 8. Base 8. So this is as a 33 base 8 means as a offset number is given as 33 base 8. So we have to calculate the binary and the decimal equivalent. Okay, so firstly we have to change the offset to the binary. Offset to binary. So this is a conversion from the offset to the binary. So how to change the conversion? Firstly, you see that 33 base 8. So this can be that you can 33 is a first is 3, second also 3. So you can use it as 3 and 3. Firstly, you divide it separate 33 base 8. So you have to separate them first 3 and second 3. And then the 3 are divided by 2. So there, first 3 divided by 2. So you 3 divided by 2. So there. Result 1, remainder 1. Okay, so another 1 divided by 2. So there will be no result. No result and remainder 1. Then you write from here to here. So there will be 0, 1, 1, 4. Okay, another 3. So this is the first 3. And second 3 divided by 2. So there will be result 1 and remainder 1. And the 1 is divided by 2. So result 0, remainder 1. So you write this way, that will also be the 0, 1, 1. So therefore the weekends are represented as 33 base 8. 33 base 3 base 8. 33 base 8 will be the weekends like this becomes as 0, 1, 1 and 0, 1, 1 base 2. So that way 33 base is equal to base 2 is 011 011. So this is for the offset to the bidigital conversion. Another one is an offset to the decimal conversion. So that will be the 33 base 8. So first 3 is, so this is the first 3, second 3. So first 3 multiply 8 power 1. So this is for the first position, and this is for the 0 position. And because the first positions are 3 multiply 8 power 1 plus another 3 multiply 8 power 0. So then 3 multiply 8 power 1 is 8, 3 multiply 8 power 0 is 1. So 24 plus 3, so this is a 27. So 27 base 10. So therefore the 33 base is equal to 27 base 10. So this is the order to the decimal conversion. Order to conversion means that you have to see that this 3 is a 0 position, this 3 is a 1 position. And because of the for the 1 position, 3 multiply 8 power 1. For the 0 position, 3 multiply 8 power 0. So then 3 multiply 8 power 1, so 3 multiply 8, 3 multiply 8 power 0, so 8 power 0 is about 1. So because of this one, so you call that 3 multiply 8, 3 plus multiply 1. So the 27 plus 3, you call that 27 base 10. So this is for the decimal conversion. So this is this problem, we change the order to binary conversion. For the order to binary conversion, you have to separate the number. 33 base 8, so first 3, second 3, you separate. And first 3 divided by 2, so you call it 011. Second 3 divided by 2, you call it 011. And you write again 011, 011. So this is the order to binary conversion. Order to decimal conversion, you have to find out where is the location of the 3. So the first 3 is the location 0, second 3 is the location 1. Because the location 1, 3 multiply 8 power 1. And second 3 is the first 3 is the location 0, so 3 multiply 8 power 0. So then we see that 33 base 8 is equal to 3 multiply 8 power 1 plus 3 multiply 8 power 0. So then by solving this one, you call it 27 base 10. So this is for the binary to the order and the binary to the decimal conversion. So another one with the hex decimal system. So hex decimal system, well, we can write the thing and 10, so base 10. That way we just Cn multiply 16 power n plus Cn minus 1 multiply 16 power n minus 1 plus, so then calculate C2 multiply 16 power 2 plus C1 multiply 16 power 1 and then C0 multiply 16 power 0. So this is for the hex decimal equivalent. Hex decimal number. So then we just hex decimal number 1H, 2H, 3H, 4H, 5H, 6H, 7H, 8H, 9H. So this is 1 to 9. 1H, 2H, 3H, 4H, 5H, 6H, 7H, 8H, and 9H. So 10. There's a no 10. Instead of 10, you have to write an AH. 11 is a BH. At 12, we use a CH. 13, we use a DH. 14 is a EH. And 15 is a FH. So those are the hex decimals. Hex decimals are start from 1H, 2H, 3H, 4H, 5H, 6H, 7H, 8H, 9H. So 10 will be AH, 11 will be BH, 12 will be the CH, 13 will be DH, 14 will be EH, and the 15 will be the FH. So those are the hex decimal number. So we have to find out decimal equivalent of 47H. 47H means 47H. So you don't need to worry about the H because H is only the represent as a hex decimal. So 47H is similar to 47. Okay, 47H is the same as the 47. The H does not indicate any number. This is a hex decimal 5. Okay, so 14 and 7. So 7 is location 0 and 4 is a location 1. And because of this one, 4 location 1, 4 multiply 16 power 1. Plus 7 location 0 is 7 multiply 16 power 0. So that will be 4 multiply 15 plus 7 multiply 1. So that will be 64 and 7. So 64 plus 7 you got calculate, that will be 71. So 71 and a base 10. So 47 is equal to 71 and a base 10. So we got. And similarly, 30 dH. So 30 dH will be 30. So 3 is a let's see, location 1, 0 is location 0. So that will be 3 multiply 16 power 1 plus 0 multiply 16 power 0. So that will be 3 multiply 16 plus 0 multiply 1. So that will be the answer will be 48. So this is a 16 power 0 is 1. So 3 0. So yes, because of 13 dH. 13 dH. So dH are similar to 13. So dH is 13. 30. That's where we get these are dH. Okay, 30 dH similar to 30 D. So 30 D is a first 3. So first D is a location, this D is a location 0, the 0 location 1, 3 is a location 2. So 30 D. So this is a 30 D is equal to similar to 30 D. So 3 is a location 2, 0 location 1, D is a location 0. So you multiply, 3 multiply, 3 is location 2, so 16 square. Plus 0. So 0 is a multiply with a location 1. So 0 is a location 1. So 0 multiply 16 power 1 plus D. Okay, D is you see here, D is a 13. So 13 multiply 16 power 0. So that will be the 3 multiply 256 plus 0 multiply 16 power 0 multiply 16 plus 13 multiply 1. 16 power 0 is 1. So you solve this one, so that way you got a 781. 781 and base 10. So 30 dH equal to 781 base 10. But 30 dH you can rewrite 30D. So the D is at location 0, 0 location 1, 3 location 2. Because of 3 location 2, 3 multiplied 16 power 2. Because of 0 location 1 or 0 multiplied 16 power 1. And D value is normally 13. So 13 multiply location 0, so 16 power 0. So by solving this one, you got the things are 3 multiply 256 plus 0 multiply 16 plus 13 multiply 1. So you got a 781 base 10. So this is for a 30DH. And another one with the A2FH. So A2FH, you can simply write the A2F. So A is similar to 10. 10 and 2. So this is 2 and F. So F is equal to the same as here. F is equal to 15. So this means 10 is located at location 2. So this is for the 10. So 10 is so you can see that 1 0, and this is a 2 in the F. Okay, this is 10 to F. 10 to F. So 10 to, so F is the same as 15. 10 to 15. So in this case here, 15 is, the whole 15 is at location 0. The whole 2 is at location 1. The whole 10 is at location 2. Because the 10 is not originally is coming off from the A. So because the A is a location 2 is a location 1, and F is a location 0. So the A's we represent in the fact A is similar to 10, and 2 is 2, and F is similar to 15. So this is the 10 is a location 2 is location 1, and 15 location 0. And after that, 10 is location 2, so 10 multiply 16 power 2. 2 location 1, so 2 multiply 16 power 1. 15 location 0, 15 multiply 16 power 0. So this is a 10 multiply 256 plus 2 multiply 16 plus 15 multiply 1. So by solving this one, you got the thing is 2607 base 10. So this is ways out. We change as our head decimal to the head decimal conversion. Alright, so we find a decimal equivalent. So head decimal number given, and we need to find a decimal equivalent. So the head decimal to decimal is you have to multiply with 16. And so decimal to head decimal, you have to divide by 16. So there are two things. Head decimal to decimal conversion. So head decimal to decimal. So that's multiply with 16 power n. And decimal to head decimal. So divided by 16 power n. So this is for the equation. So head decimal means the multiply with the 16 power n, decimal to head decimal is divided by 16 power n. So this is for the head decimal to the decimal conversion. Okay, so we need to find the head decimal equivalent of the 20s are base 10, 29 base 10, 175 base 10, 3012s are base 10. So we have to find the head decimal equivalent. So firstly we calculate for the 29 base 10. So 29 base 10 is this 29 is divided by 16. So you divide that 29 16. So there will be the 1. So the result 1 and remainder is 13. These are remainder 13. Result 1 you can write a 1. Remainder 13. So remainder 13 is a 13 you see here. 13 is the same as a D. So there will be the D. 1D. So we represented the head decimal. Because of to indicate the S decimal, at the end you put the H. So 29 base 10 is equal to 1DH. So 29 base 10 I explain again. 29 is divided by 16 because we convert the head decimal to head decimal. So the 29 base 10 are decimal system. We want the head decimal. So 29 is divided by 16. So 29 divided by 16, you got the result 1, remainder 13. So result 1, you just write a 1. Remainder 13, you see the table. 13 is similar to D. So the 1D. So to indicate the head decimal, at the end you have to put the H. So there will be 1DH. So 29 base 10 equal to 1DH. And also 175 base 10. So 175 base 10 you need to convert to the head decimal. So the 175 divided by 16. So you see that 175 here, 16. You can divide it 10 times. 1 you got the 15. So it does a 15, so you cannot divide again. So this is 10. So 10 is a result and 15 is a remainder. 15 is remainder. 10 is a result. 15 is remainder. So the 10 is result and the 15 remainder. So that you can write 10 plus 15 by 16. Okay, 10. So 10 is you see the table, 10 is a A. So write A for the 10. 15 is S. So write S for 15. And to indicate the head decimal, so N you put the H. So AFH. So this is the 175 base 10 is equal to AFH. And also that we find the head decimal equivalent of the 3412 base 10. So in this case, you divide the 31412 by 15. So we substitute here 3412 15. So you divide the 3412 16. So you can the answer will be that you this is 213. 213. So firstly you can solve it as base 4. So this is 4. So this is the I divide here 3412 16. So you got a 2, so that's a 32. That is so 21. 21, so you divide by 1, so this is 16. 16, so this is a 52. and 3, so you got 48. So base will use that 4. So that's 213, remainder 4. Because of this one, 213 plus 4 by 16. Okay, so in this case, you can write as 213, the 4 by 16. So in this case, you can see here. Here we see that remainder. So you don't need to worry about the result. You only need to worry about the remainder. The remainder is 4. So this is you just write a 4. So this is 4. 412 base it in. And then this 213 is divided by 16 again. So 213 divided by 16. So 1, you've got the 16, so this is the 53. And 3, so you got the 48, so you got the 5. So there will be second these are you have to divide 213 by 16. So 213 by 16, so you got the 13 plus 5 by 16. Okay, so in this case result is a 13, remainder 5. So you just write remainder 5. Okay, then 13 is divided by 16. So cannot divide. So only the remainder is a 13. So therefore the 13 divided by 16 means result 0 and remainder 13. So in this case you have to write the remainder. Remainder is coming out 13. Remainder coming out 13, but 13 you need to interpret. 13 is similar to D. So D. Okay, so in this case as you can see the D remainder, 5 remainder, 4 remainder. So you go to the this direction. So you have to go direction, so D 5 4. Okay, D 5 4. So this is the head decimal. So at the end you have to put the 8. So D 5 4 8. So then we will start 3 4 1 2 base 10 is equal to D 5 4 8 for the head decimal system. It is number. So all the digital numbers are we write in the positive number. So that this one you can see that 33 8. So positive 33 8. So 781 base 10. So this is the positive 47 H, positive 30 H. And also this one you got the positive D54 H. Those are the positive number. But in the numerical calculation, sometimes you can see the negative number. So there are the two ways to represent this negative number. So this is the negative number representation that we use the 2's complement method. It's utilized to represent the negative number. So this is ways that we use the 2's complement method. So the first method, so they are the similar method. So this is the method 1. Okay, so we find that minus 1 1 1 0 1 1 2. So represent to be represented by two completion method. Okay, so we want to represent the minus 1011 base 2. Okay, so method 1. Method 1 is subtract from the. So this is the 1011 base 2. So this is the 4. So you have to subtract from the So this is the 1011 2. It's subtract from this one. So this is the 1011. So you put a 0 here, 0 here, 0, 0, and also this one is divided by 10. So you subtract from the 1011. 1011 needs to be subtracted by 100000. So because of you need to subtract, so you have to put a borrow. So this is 0 and 1. 0 and 1, so you cannot subtract. So you need to borrow. So you have to borrow so that in the number system you borrow the 10. But decimal system, you have to borrow the 1 0. So that because of this one, you borrow the 1 0. So 1 0 is that this one you borrow. So this one coming as a 1 0. Okay? This 1 0. So this 1 0 minus 1. This 1 0 minus 1. You got a 1. Okay? And then this is 0 and 1 again. So you need to borrow. So in this case, you have to put this 1 here. So 1, so this is 1 0. 1 0 minus 1 is you got it. So this is a 1. So this. So when you borrow the 1 0, the only thing you let is only 1 left. So this is you borrow the 1 0 here. 1 0. So 1 0 that you started the 1. Then with 1. So 1 0 you started the only 1 is left. Okay. So only 1 left. Because similar to the here. 2 by 3. 22 minus 3. What will you do? You started at 10. So you borrow 10. So 10 minus 3 you got as 7. So 7 plus 2 will be as 9. Okay, 9. So this is a 1. So this is by this way you subtraction. Subtraction is 22 minus 3. You borrow the 10. 10 minus 3 is you got a 7. Okay? The 7 and 2 you add, so you got as 9. So here 2 is a 10 borrowed, so only 1 left. So this is all the 19. 19 left. So this is the numerical subtraction. And same like here, you borrow the 10. So 10 minus 1. 10 minus 10 minus 1 is you got the result 1. And so 10 is subtract, so only 1 will be left. So this one and this one, you make the subtraction. That will be 0. And here 0 and 0. So 0 and 0 subtract 0. Here 1. So when you start, give the borrow, this 1 0 0 only left with the 10. Okay? So this is 1 0 minus 1 will be 1. So you got the 1 0 0 1. So this is a 1001. So after this you got a 1001. 10 and this one is a okay, so this one is you subtract here to 1 and 1011. So firstly you subtract this one you got subtract 10. So 10 minus 1 is 1. So this is 1. So this one will be 1 and 1, so you got a 0. So this one is you subtract as so this one is this is the 1. This one becomes 0 and this one 1. So this one is letter 1 and this is 1. 1101. Because you add again 1011 1001. So you add 1 and 1 to 0. So this is a 0. So this is 1 and 10. So this is what we got. So 10101 we got. So this is for us two completion methods. We don't separately represent a negative number or a positive form. So this is in this case really is a negative number, but we represent by a positive form. Yes. So this is for the side number. Side number. This is only things we do. So don't need to compute too much. But only thing what you do is in the digital system, negative numbers are usually represented by a positive. So this is for the negative side. They call it a sublet method. So in this case, this digital computer system is calculate itself, but instead of the minus 10112, we usually represent this way by the two completion method. The most easy method, so this is the method 2. So we don't subtract. Instead we use the things to say, first you have to subtract 1 0 0 0 0 0, and then you put a 1 0 1 1. Okay, so what you do is that this another method is more easier. First number is that you just write the same number. This is 1. You just write the 1, same number. Okay? And then second one. Second one is you just write the opposite number. Just write the opposite number is, here is originally 1. So here you just a 0. You just write the opposite. And this is 0. You just write the 1 opposite. Here 1. You just write the 0 opposite. And add 1. So that way you just have 1 0 1 0 1. So this is also the second complement. So this method you don't need to worry about subtraction. You just write the order 1 here. So just 1. The second one just write the opposite. So 0. The 0 just write the opposite 1. And final one just write the opposite 0. At the end, you just put the additional 1. So 1 0 1 0 1. So that will be 1 0 1 0 1. So this is for a two complement method. So this is a computer started by this way. Because computer does not make that does not have a human brain. They make that a regular method. Human brain you borrow or subtract, but computer does not understand borrowing and subtracting. Only follow the same procedure. So in this case, the 1 0 1 0 1 0 1 1 you need to represent. So in this case, what we do is the first one you just write 1, second one change, third one change opposite, the other one you change, and then finally you add 1. So this is a two complement method. So 1 0 1 0 1. So the minus 1 0 1 1 base 2 is similar to 1 0 1 0 1 base 2. This is two complement method. So we follow this method to the calculation. So instead of the borrowing or the thing, you just do the thing. So this is the two complement method. And similarly, you also need to find the program to represent the 1 0 1 0. Two complement method. So this is two complement. So what will you do is that you just write the 1 0 0 0 0 0 and then 1 0 1 0. Okay, so we just write, and after that, first number you just write the same number. First number you just write the same number. So 0. Second number 1. So in this case, they start with another 1. So before reaching the any first one, you just write the same number. Here is you see this first one you just write the same number and then you change. Here is that 1 is here. So before reaching the 1, this 0 you just write the 0, and this is the first one. The first one you also write the same number. So this is the same number. So this is the before reaching the first one from right to left, just right, the same number. After that, after the first one, then write the opposite number. So this is the formula. Before reaching the first one, from the right to left, just write the same number. No. Before reaching the first one, Before reaching about here is from the you coming from the left to right. Here first one. First one you get the same number and then you got the opposite number. But here, go from the left to right. You haven't see the any first one yet. 0, so just write the 0. Same number. First one, the same number. After that you got the write the opposite. So after the opposite means this 0 will become as a 1. 1 become a 0. Finally add a 0. So this is the L1. So this is a 1 0. So this is the opposite. Write the opposite. So this one represents 0 and add the 1. Add 1. So this is a same. So then we will get minus 1 0 1 0 2 is equal to 1 0 1 1 0 2. This is a two complement method. Two complement method is you count from the right to left. Right to left. First case is right to left. Before reaching the first one from the right to left, just write the same number. After the first one, then write the opposite number. So this is the right to left. Right to left, you see the first one as C. So just the right same number here. And after the opposite, so this is 1 become a 0, 0 become a 1, 1 become a 0, and finally you add a 1. So there's a 1 0 1 0 1. So this one is at 0. So before reaching the 1, just write the same number, and this one just write the same number. After this 0 become an opposite 1, 1 become a 0, and the final one is an S. Just add the 1. Final one is the addition 1. Ever add the final one. So then, finally, H 1 at the front. So this is the rule you utilize. Okay, this one I again, you start from the right to left. So first you got the first one, just write the 1. And after that, this one you change to 0 opposite 1. The 0 you change to opposite 1, the 1 change to 0, and finally you add 1. So this is 1 0 1 0 1. And this program starts from the right to left. So we haven't seen any 1 yet. Only see the 0. Just write the 0. And finally, first one is also the right the same one. First one also write the same. And after that, this 0 is change to 1 change to 0. And so finally you add the 1 at the front. So this is a 1 0 1 1 0. So this is the two complement method. So computer we sort like this way. They look at the front is a right to left, first they check the 0 or 1. So long as they haven't seen that 1, they just put the same number. As soon as the first one, they change they write down the same number, and after that they change. So this is what we calculate. So this is the two complement method for the zeros or ones or the negative representation. Normally we use the subtraction, but subtraction is complicated. So even if you do the decimal is a computer, this is a binary very complicated. Don't use this method. Only we use the two complement. So this is what we saw.
You always put this.
The first is I already talked about it. This is the positive. Positive is integer. Integer means the full number. And then this one is we represent a negative number. So negative number we use the two complement method. And then another one we also use the decimal number. The decimal is a fractional binary number. Fractional binary number. So in this case, our fractional binary number is a formula and then it's equal to P1 2 power minus 1 plus P2 2 power minus 2 plus P3 2 power minus 3 and then goes the Bn 2 power minus n. So this is a fractional number. So in this case, our n then is equal to base 10 number less than 1. This is called the binary fractional number. Binary number and then it's going to B1 2 power minus 1, B2 2 power minus 2, B3 2 power minus 3, and up to Bn 2 power minus n. So those are the fractional binary number. So and there is a base 10 number less than the 1. Okay, so we need to find the binary So program, find the base 10 equivalent of the binary number. So there we just are 0 white decimal 11010 base 2. So this is what we need to find the base 10 equivalent of the binary number. Okay, so firstly we can write and 10. Okay, first one. This is first one, 2 power minus 1. And second also 1, 2 power minus 2. Third number is 0, 2 power multiply 2 power minus 3. Fourth number is 1, 1 multiply 2 power minus 4. And fifth number is 0, 0 multiply 2 power minus 5. So this is the way we calculate. So this means this is the first one, this one here. And this second one. The third one is 0, and then with the 2, 1, this is 0. So this is after the decimal you see the 1. So 1 multiply 2 power minus 1. After that you see the 1 multiply 2 power minus 2. After that you see the 0, 0 multiply 2 power minus 3. After that you see the 1 multiply 2 power minus 4. And then finally you see the 0 multiply 2 power minus 5. So that will be the 1 multiply 2 power minus 1 plus 1 multiply 2 power minus 2 plus 0 multiply 2 power minus 3 plus 1 multiply 2 power minus 4 plus 0 multiply 2 power minus 5. So we got. Okay, so 2 power minus 1. So 2 power minus 1 is 1 divided by 2. So 1 multiply 1 divided by 2. So this is 1 divided by 2 square. 0 divided by the 2 power 3. So 1 divided by 2 power 4. And 0 divided by 2 power 5. So then we just have half 1/4. So there is 0. So 1 by 16 plus 0. So this is you subtract and you calculate. So then we just have the answer will be 0.8125. Yes. Yes. So this is 0.10102 is equal to 0.8125 base 10. So 0.11010 base 2 is equal to 0.8125 base 10. So by this you can calculate. You can see the fractional binary decimal. So that 0.110102 you want to convert to the decimal, so you have to divide. So 1 multiply 2 power minus 1 plus 1 multiply 2 power minus 2 plus 0 multiply 2 power minus 3 plus 1 multiply 2 power minus 4 plus 0 multiply 2 power minus 5. Then you solve the thing, so you got the 0.8125 base 10. So this is for the fractional binary to decimal conversion. And the next one will be the fractional decimal to binary or the hash decimal conversion. So we solve another problem. Find the binary octet and hash decimal equivalent of 0.3125 base 10. So we have to calculate. Okay, so first method is we need to start. This is for the decimal number. Decimal number is 0.3125 base 10. This is the decimal number. So you need to convert to the binary, then octet to the hash decimal. So in the calculation, the first step is you first convert to the binary part. And then based on the binary number, then you will convert to the octet and the hash decimal. So the octet and the hash decimal conversion will be based on the binary number. So So first step is you have to convert to the binary number first. So how to convert to binary number? So you have to binary the 2. So you need to multiply with the 2. So that this is what we calculate here. 0.3125 base 10. So you need to multiply with 2. So 2 multiply 0.3125. So multiply 0.3125 means 0.6250. 6250 means that we haven't got the any integer yet. So no integer, just write the 0. This one is 0 because there's no integer. Because of this is a decimal. So we only you see the number after the decimal. Before the decimal there is 0. Before decimal 0 means this base 1 is equal to 0. So because before decimal there is only 0. So this is the base 10. Okay, then you got a 0.6125. 0.625. So this is 2 also again multiply with 0.6250. So 2 multiply 0.6250, you got about 1.250. Okay, 1.250. So what you have to do is, you take out this one. So this is the base 2 is equal to 1. So only 250 left. So you just put the 0.250. This 250 you write here and then multiply it 2 again. Okay? And multiply it to the 2 multiply 0.250, so you call it 0.500. So there is a space 0. Before the decimal there is space 0. So that way bit 3 is equal to 0. Okay, bit 3 0. After bit 3 0, you call it 0.500. So this is a 0.500 take out here. 2 multiply 0.500. So therefore you get 1.0. Okay? 1.0. 1.0 means in this case this is a bit 4. The bit 4 is 1. So after that you end at the 1. So you don't need to do any more. So end at the 1. So after that you write, after end at the 1, you can write the thing. So you count from down to here. The format number is a 0.B1, B2, B3, B4. This is the format. Base 2. 0. Bit 1, bit 2, bit 3, bit 4 are base 2. So therefore that will be there. Yeah. Bit 1 is 0. Bit 2 is, so this is a 0 point. 0 point, bit 1 is 0. 0, bit 2 is 1. Bit 3 is 0, bit 4 1. 0.0101, base 2. So this is for the format. So therefore, 0.3125 base 10 is equal to 0.0101 base 2. So this is for the binary equivalent. So first step we calculate the binary equivalent. So this is the binary equivalent. Binary equivalent is 0.3125 base 10 is equal to 0.0101 base 2. Okay. Then we have to find to the change the offset. To change the offset. So firstly you just write 0.0101. So this is the original number. To change the offset, you have to add the 3 binary bits. So you have to combine the 3 binary bits. To change the offset, 3 binary bits are to be combined. To change the order, 3 binary bits are to be combined. So now we will how to combine. You just write again 0.0101. So you have to combine the 3 binary bits. 3 binary bits after the decimal, you see the 010. So this is the 3 binary bit. So this is 3 binary bit. Okay, so 3 binary bit. So after the decimal, you just combine it 0, 1, 0. So this is 3 binary bit. So only you see the 1. Why is it you don't get the any 3, so you have to put the another 2 binary bit. To put the 2 binary bit, you have to put the 2 0. So let's put the 2 0. Put the 2 0. So this is the 4. Then this you call it by this way you can call it another 3 binary bit. So that will that set numbers is 0.010. This is the first 3 binary bit. Another one is 100. Another second binary bit. So these numbers we can rewrite. Then we use 010 and 100. So this is called 0100 and 100. So this is 010 and 100. So after that, this one you change with okay, or there's a what we do is 010 means it's 0 multiplied 2 power 0. And this is the second place. So this 010, that way the place 0 place. This is the 1 place. And this is the 2 place. And also this one is 2 power 0 place. So this is a 2 power 0 place, and 2 power 1 place, and 2 power 2 place. So also this one is a 2 power 0 place, and this is a 2 power 1 place, and this is 2 power 2 place. So after that you see the thing, 0 multiplied 2 power 2 places, 0 multiplied 2 square, plus 1 multiplied 2 power 1, plus 0 multiplied 2 power 0. So that way you get 0 multiplied 4 plus 1 multiplied 2 plus 0. So that way we just only thing the thing you got is you got a 2. So 010 you got a 2. And similarly 100. 100 means 1 multiplied 2 power 2 plus 0 multiplied 2 power 1 plus 0 multiplied 2 power 0. So that way you get 1 multiplied 4 plus 0 multiplied 2 plus 0 multiplied 1. So you got a 4. 2 4. Okay? 2 4. 2 4 means 0 1 0 is similar to 2 4. So that way that's equal to 2 4. 2 4. So this is the space. So because of this one, you can write a thing. So this one was an odd number will be there 0.24 basic. So that will be the order equivalent is 0.24 basic. This is the order equivalent. This is a binary equivalent number, so that you got the 0101. So 0101 you have to combine the order. Order means you have to combine the 3 binary digits together. So 010 you can combine, but only one left. So to put the only one, you have to put another 2 0. So this is a 010 is a first order digit, and 100 is another order digit. So that this 010 you change it as a number. So the 010 is a 0 is a 2 power 2 place, 1 is a 2 power 1 place, and 0 is 2 power 0 place. So this is 0 multiplied 2 square plus 1 multiplied 2 power 1 plus 0 multiplied 2 power 0. So if you solve this one, you got it finally is a 2. And similarly 100. So 100 is 1 is a 2 power 2 place, 0 is a 2 power 1 place, and a 0 is a 2 power 0 place. So that way 1 multiplied 2 square plus 0 multiplied 2 power 1 plus 0 multiplied 2 power 0. So by solving this one, you got the thing is 4. So that way that's 2 4. 2 4. So 2 4, but this is a decimal system. So 0.24 base 8. So this is the order equivalent. So order equivalent you combine with the 4 digits. Okay. Another one is a hex decimal. To change hex decimal. To change to hex decimal. Hex decimal is, this is the original number is 0.0101 base 2. This is called the original number. Here, So this one is that you change the hex decimal name. The order is that you have to combine the three binary digits. The order system, you have to combine the 4 binary digits. So to change orders, 4 binary digits are to be combined. So 4 binary bits are to be combined together the order system. So this is the hex decimal system. So 4 binary bits are to be combined to the change the hex decimal system. Okay, so now we change the hex decimal system. Hex decimal system is now using 0.0101. So the 0.0101. So first number. So this is the 4 binary bit. So this is about 0101. That will be the 4 binary bit. So this is the 4 binary bit. 4 binary bit. So just second four that you don't see anything, just put another 40. 0000 you put. Because you don't have any bit, so you just put a 0000. And then you see that the thing. The best we done is 0101 and 0000. So this one way is 2 power 0 place. The 0 way is 2 power 1 place. 1 way is 2 power 3 place. 0 way is 2 power 4 place. Also this one way is this 0 is 2 power 0 place. 2 power 1 place. 2 power 2 place. 2 power 2 and this 2 power 3 place. 2 power 3 place. So therefore this one you multiply. 0 multiply 2 power 3 plus 1 multiply 2 power 2 plus 0 multiply 2 power 1 plus 1 multiply 2 power 0. So then we means this is 0 plus 4
Yes.
plus 0 plus 1. So then we is 5. And second we say here. So this is a 0 multiply 2 power 3 plus 0 multiply 2 power 2 plus 0 multiply 2 power 1 plus 0 multiply 2 power 0. Everything will be 0. So then we will 0.50. So this will 50. This is for the hex.
So this is the ways how we convert the hex decimal system. So this is a 0.0101 is equal to 0.0508. So here we see the designing the decimal gate system. So we are using the decimal gate system. We are designing the decimal gate system to provide the alarm system. So this you see the alarm system. So this is the pressure we can sense, and then we can convert it to the temperature. We send the level as well as the temperature we set. High level will be the 1, low level is a 0. Similarly, the high level temperature will be 1, low temperature is 0. So alarm can be this 1 is on, 0 is off. So this is the ways how we have to send the level and the pressure. So by sending the level and pressure, we have to use the gate. So this is a low level is a bar, high level is a A, the pressure is a low level is a B bar, high level is a B, and temperature is a low level is C bar, high level is C. In this case, all the had to be combined as of function. So A bar B plus AC plus ABC bar, that will be the outputs at D. So this outputs are alarm system. So this output system equation, we can utilize a digital gate. So that this is that we use a digital gate, level A, B, C. So for the A bar, you have to put a NOR gate, and you have to combine the A bar B, so that will be the AND gate. And when you addition, you have to use the OR gate. This is the ways how we convert this function. We can use a digital gate to get the output function. So that this way that we have to write down the function and also the digital function, digital function the equation, and then those function equation need to be represented by the digital gate. And since that we also utilize the programming logic controller, the programming logic controllers are the switch the location or solution of control system. So those are solution of control system. Those have to be provided by the PLC system. So in this case, our PLC system will be the user, the competitor, and also the then PLC system. We use the competitor, and then we can provide this a LAN system. So those are the various systems. So there will be this topic we can see there are a construction of the various type of the competitor, and also the historical competitor and revision problem. So those things we will solve later. So at the moment that this today lesson, what I did to give you is I give you the digital logic system, binary number conversion system, and then I talk about the digital equation to represent the logic gates.